We are recording now, so welcome to week 9, day 2. So prior to class starting, we talked about the associate's degree in computer science. It's pretty easy to get. If you've taken 40, 41, 26, and 45, that's it. Then like 5A or 5B, or 2A or 2B, or 4A or 4B. It's pretty easy to get an AS. And so you just go on to WebAdvisor and apply for a degree. That's it. And then you get a AS. Yay. Cool. More, might as well. Right? Might as well. All right, so today we're going to be continuing our discussion of topics. All right, so talk a little more about floats, and we're going to learn the IEEE 754 format for floating point numbers finally, so you kind of understand what's going on there and why you can't just right shift them to divide by 2. Okay, so video image is blocking that, huh? Let's turn off that, and let's turn off that. There we go. So, so what's happening with your homework assignment right now is, so you moved your date past the deadline. Yeah, that's funny. Degree page, yeah. It's all good. It's all good. If you miss the deadline, it just gives you the degree a semester later. Trust me, when you're my age, like I literally don't know when I got my degree, which sounds weird. Like, why would you not know when you graduated? But I graduated every year. At UCSD, all you have to do is go into the bookstore. And they don't check, like the bookstore doesn't know if you're going to graduate or not. So every year I'd go into the bookstore, say I'm graduating this year, and put down the $20 or whatever for my regalia. And then when graduation rolled around, I'd go in there and put on a graduation cap and robe and walk around campus, and everyone would applaud me, and we would go to the graduation ceremony, which was always fun. They always had like a top tier speaker come in. We had, I think Bill Clinton spoke one year, although that year I missed it because I was grading finals as a TA. Maya Angelou, I think, was supposed to come and canceled. She actually just died this year, I think. I saw Patch Adams speak. Patch Adams being the comedian doctor, played by Robin Williams in a movie with the same name. And this guy, kind of an asshole, turns out. So, yeah. Wasn't as amusing as I thought it would be. He did moon the audience at the end, so he dropped his pants and exposed his buttocks to all of us in the crowd. Who else did I see? Oh, Erwin Jacobs. Do you guys know who Erwin Jacobs is? This dude? Yeah, at UCSD. He's the founder of Qualcomm. So fairly well-to-do person, $1.2 billion. Yeah. Fairly well off. And Qualcomm is like right next to UCSD, so a lot of our EEs work there. I actually worked for Qualcomm technically on a project, sort of through a grant, so it wasn't directly for them. Viterbi, I've seen Viterbi speak as well. So Viterbi developed the foundation of modern cell phones, I guess you can call it. There was obviously a lot of people that did it. He was a professor of electrical engineering at UCSD and proposed the Viterbi algorithm to decode convolutionally encoded data. It is widely used in cellular phones for error correcting codes and many other uses as well. So he helped develop CDMA. And so back in the day, there was CDMA and TDMA, which were kind of competing cell phone standards. 3G, for example, used it. So if you ever used cell phones back in the day, there were two different spread spectrum algorithms. And yeah, so I saw him talk. Cool dude. Anyhow, so the point is, like, I would just graduate every year. He didn't speak at graduation. He spoke at the local electrical engineering department. They gave talks. So I actually don't know when I graduated technically, because every year I just do it. It was just kind of kind of a practical joke for me. But also I kind of didn't know because it really depended on when I got my thesis done, and so I kind of, like I had my coursework all done. It just was dependent upon me defending my thesis, and so that was up in the air. And so I don't know. It was just kind of fun for me. Yeah. All right. So if you want to get your associates, I'd recommend it. Why not? Go for it. All right. So 3D array axis. So this is what we are doing for the current assignment. You've got 3 planes of data: a red plane, a green plane, a blue plane, and like we talked about last time, sometimes they'll interleave the colors, so you get a red, a green, a blue, a red, a green, a blue, a red, a green, a blue, like the PPM format that we talked about last time, which PPM is a terrible format. You should really use the CImage library to write JPEG and things like that, because it will compress it. It will compress it much, much more than this kind of stuff. But PPM is simple enough that you can read it as a human, and you can write programs to output it really, really easily. Okay, so so Neon has interleaving commands. We don't need to worry about that for this assignment. So so this is row major ordering. I think we've gone over this enough times, but yeah, basically, if you're gonna, for a 1D array, just the one thing to remember, always remember, guys, is that whenever you access element 50, it's going to be the base plus the offset, and the offset is the index times the size of the data type, right? So for an integer array, and this is what was causing a lot of problems for you guys last time, was that you would be trying to access element 50, and so you just add 50 to the array pointer. And this would actually work in C++, right? In C++, if you added 50 to the array, it would go 50 integers to the right. But in assembly, you have to make sure you multiply by the size of the data type. So you had to go 200 bytes to the right. So accessing element 50 is accessing memory at R plus 200. You guys all comprehend that by now? Hopefully. I mean, I've been kind of hammering this point a lot this semester, so. Okay. And then if you want to, cool. And then if you want to go down, if you have a 3D array, then every time you go down a row, this is plane, row, column. Every time you go down a row, you move a number of bytes to the right equal to the width, right? So the number of columns. So going down one row is equal to going columns to the right. And when you go down a plane, you go down width times height to the right. So if you have a 10 by 10 image, then going down to the next plane is moving 100 bytes to the right, assuming they're unsigned chars, 1 byte per element. Okay, so yeah. All right, so we're going to be talking about floats today. So basic ARM32 doesn't have any reference to floats at all. All ARM processors can handle ints. They can handle 32-bit ints, and 16-bit ints, and 8-bit ints. 64, maybe. But floats, maybe. So when you write C++ code on a new platform, and if you're on like an Intel, you don't have to worry about this. But if you're like going to be doing embedded programming, embedded programming is like if you enjoy this class, then maybe embedded programming is for you. So you're writing code on like these really limited systems, right? And these things can program like, I don't know, microphones and Game Boys and like really, really weak ass stuff, remote controls and stuff like that. And so there's a whole, industry, and it's a really big industry. Like where people program things in sort of limited. These things are often very limited. Like you've got like 100K of RAM, you know, that kind of stuff. And so in systems like that, whether or not you actually have floats is, you know, it's up in the air. You know what I mean? And so you have to do things like check, do I have a floating point unit? You know? And so, you know, when you're on one of those platforms, you need to know, am I on a system that has hard floats or soft floats? So what does that mean? What is the difference between a hard float? I'm going to write that down here. Hard float versus soft float. It's like the difference between hard touch and soft touch. A hard float means the system has an FPU. So in other words, it has hardware that actually can handle floats. Okay. And then soft floats means it doesn't. So it has to emulate floats using its... And so the problem with soft floats is like, let's say you do, let's say you're in C++, you see like float f equals, you know, 4.2, and then you say f, you know, plus equals 10.1. You can do this using regular integer assembly. If you open up your textbook, there is, you know, 80 lines of assembly code that will emulate floating point multiplication and division and stuff like that. But it's really, really slow. So if you have a soft float system and you know, use floats, then your code will be 80 times slower than it should be. So if you can avoid it, don't. You guys understand? So if you go onto a new system, you can always type lshw. lshw list, you know, it's like the ls command, but for hardware. And then it will tell you, yeah, okay, we gotta, did I connect it? This is not the Raspberry Pi. Let me try this one more time, connecting to the Raspberry Pi this time. Okay. lshw, type through more. And yeah. And so we've got VFP. So we've got vector floating processor and Neon, and vector floating processor version 3, and vector floating processor version 4, and vector floating, you know. So this will tell you which capabilities your CPU has on the CPU. So I've got 4 cores here. Each core counts as a CPU. That's why I kind of use that term interchangeably sometimes. Perhaps I should not, but a core basically is a separate CPU. It tells you how much RAM you have, that kind of stuff. So if you ever do embedded systems programming, then this is actually going to be something you would have to check, which is like, you know, do I have hard floats or soft floats? Okay, so floating point math can be very slow. If you're going to be multiplying an 8-bit value by floating point number, and then you put it back into a char, do you need all this precision? Right? Do you know what I'm asking? Like if you're going to be doing sepia toning, right, which is your next homework assignment, you're going to be doing floating point math. Let's say that you've got, you know, your R value is 120, and you're going to be multiplying it by that number there, 0.23430. Do you actually need all of those digits of precision? Because you're going to be storing it back into, it's going to be times equaled, right, or something like that, right? It's going to be stored back into a char. So how many bits of precision actually matter, right? Yeah. Maybe 3, maybe 4. I don't know. Especially if you're doing image processing. Like here's a question for you guys. Like if a pixel was 121, 100, 100, could you tell the difference between that and 120, 100, 100? What do you guys think? Probably not. Probably not. No. Not on 4K resolution. Nope. Yeah, exactly. And so, I mean, there are people that will like zoom in on images, like, see right there, that pixel is 1/255th off. But you know, though, if you're watching video, like, it doesn't bloody matter. You know, if you're playing a video game, zoom and enhance, yeah. If you're playing a video game, this thing's updating 60 frames a second. It's way more important that you get 60 frames a second than it is for every pixel to be 100% accurate. You know. So there are cases where this will matter. If you ever have a gradient. So let's say you have a gradient like this. In this case, the whole screen is filled up with, I don't know, not many colors. And so if you screw up on this, you'll actually see banding across the gradient. Like, you can probably actually see it right here a little bit. You can see how there's color banding. It's not quite smooth. I don't know if this will come through on the recording, but you can see that there's actually some artifacts here where it's not quite perfectly smooth. And you can see like blotting, blotchiness and things like that. So that's probably off by like one or something like that. Monitors above 24 frames per second or scam. No. Yeah. No, you can definitely see faster than 24 frames a second. If you go to a movie that's at 24 frames a second, and then you if you ever watched The Hobbit, you could watch it either at 24 frames a second or at 60. It's a very different movie. It's a very different movie when you watch it at 60 frames a second. Yeah, the human eye is weird. Like, so when people talk about the human eye and they try and put it in terms of monitors, the trouble with it is that the human eye is not like a monitor. A monitor, this section of the screen up here is the same resolution as this section down here, right? The monitor has to be at pixel perfect resolution all the way across the entire field of 4K. And the human eye has the center part, the fovea, is very high resolution, very sensitive, it's actually amazingly good. Like, the human eye can actually detect individual photons, right? There's no camera. I guess in very specific physics labs, like you might have a photon sensor that can detect a photon. The human, you're not aware of it, but when people guess, like, they'll put them in a dark room and shoot one photon at their eye, and then they have to guess if a photon hit them or not. They can actually guess better than random chance that they saw a photon. That's how good the human eye is in low light conditions. And so what happens is we don't see everything at high resolution. So the corners of our vision are kind of at blurry, low res, but good enough. If there's motion, then it's enough for us to go like, oh, there's a ball coming out. So the human eye isn't like a monitor. It's not high res across the thing. It's high res in a narrow, chunk of the eye. And so what we do is we just quickly move our eye around like this. Our eye is constantly saccading around, is what it's called. And so your eye is going like this, and then your consciousness kind of blends it all together, so you get the illusion of having high res video everywhere, even though it's not. What's happening is your eye is just going like this. And whenever you have interest in something, you look at it, then your eye just looks at it automatically. And that's why, like, people that have eye problems, like if you have a malfunction of the eye muscles, it can be very hard to read. Like, sometimes impossible to read, just because your eye doesn't, like, if you read a line and you go to the next line, if your eye doesn't move down the right amount, then it becomes very difficult, because you lose your train of thought every time you go to the end of the line and things like that. So there's like occupational therapists that work on the eye muscles and things like that. Okay, so anyway, so the point is that you could do full resolution floating point stuff, and I'm going to teach you guys that today. That's our topic for today. Like, sometimes you do want to do a full double precision multiplication. If you're sending a rocket ship to Mars, not talking about stocks now, but like actual rocket ships going to Mars, you probably want to have as much precision as you can. You know what I mean? Because like a small error on Earth can translate into missing Mars, right? So obviously you do course corrections along the way, but in general, like, yeah, you should probably use all 64 bits. You know what I mean? Like, yeah, it's probably a good case to try and squeeze as much accuracy as possible. There's definitely areas where you want accuracy, but in image processing and in video games, we don't care that much about accuracy. It should look good enough, if you know what I mean. Okay, so so how do we do floating point math without floating point? Well, what we do is we divide by a fraction of 256. Right? Can you guys think about how to do this? Using what you know now, could you do that? Without knowing any of the floating point, without knowing any of the neon floating point stuff, just using basic ARM32, do you think you guys could multiply by 13 256? Calculator mode. Yeah, 0. Thank you. Not what I wanted. Okay. So this would be the same thing as multiplying by 0.0507. Right? So this number here, by the way, this number here is 60 divided by 256. Pretty close to it. So if you wanted to multiply a number by this, if you wanted to multiply a char by 0.234303112, then what you do is you multiply it by 60. Multiply it by 60, and then right shift 8 times. That's a horrible arrow. Right shift 8 bits. Remember the double left arrow and the double right arrow are left shift, and right shift in C++. They were repurposed to be cout, and cin, right? But what they actually mean are bit shift left, bit shift right. Okay. And whether or not it's arithmetic or logical shift right depends on if you have an int or you have an unsigned int. Unsigned, yeah, whatever. Right. And so if you want to do integer, if you want to do floating point math this way, then you take x, you multiply it by 60, and then you say x is equal to x right shifted 8 times. And that will do, between these two operations here, this is the same thing as saying x times equals 0.234, right? You guys understand? And that's a lot. What does the numerator represent here? Like the 13 or the 60? That it's like whatever you're trying to multiply by. So like if your algorithm says, take the red and multiply it by 0.234, then what I do is I convert this number into a fraction of 256. And so this 60 divided by 256 is the same number as 0.234. This is big brain time right here, right? Do you guys see that? So 0.234 is more or less within a certain degree of accuracy. 60 divided by 256, 0.234. Okay. We got a little bit of error on the 5th digit, but again, you're not going to be able to see that if you're doing image processing. You know, it'll be at most probably one number higher, one number lower. You guys with me? So rather than multiplying by 0.234, you convert it into a fraction. The fraction being divided by 256. Why 256? Well, because we're doing unsigned char numbers, right? So all of our reds, greens, and blues are from 0 to 255. So, yeah. So this R value is 234 instead of 233. Scrap the code, yeah. So is it always 60? No. It's like, Rivera, what we're trying to do here is like, if our algorithm calls for multiplying by 234, then we multiply by 60 and divide by 256. Let's do another example. Let's have you guys do this. Right. So sepia toning is so the sepia toning algorithm is going to call upon you taking the red value and multiplying it by 0.393. Okay. So Rivera, what fraction is this? Convert this to some fraction of 256 using your third grade math powers. Zach says multiply by 60, then shift 8 times. Yes, exactly. So you can get floating point math using just a multiply and a shift, and so that's a lot faster than doing floating point numbers. Why do you multiply by 60? So I'm asking you, Rivera. Let's say that we're going to be, let's say the sepia, this is the sepia tone. Sepia toning is going to require you to multiply the red channel by 0.393. What fraction of 256 is 0.393? What number goes here? How do you convert from a decimal to a fraction? You guys remember? What fraction of 256 is 0.393? So yeah, 0.393 times 256 is indeed 101. So what we would do, Rivera, is if this is what our algorithm called for, and it does, it's supposed to take the red value at every pixel and multiply it by 0.393. Rather than doing that, what we're going to do in assembly is we're going to say the red value is equal to the red value times 101, and that's actually fine because if that's in a register, the registers are 32 bits, so the result of this will be a 16-bit number, right? Because even though red is an 8-bit number, the result of the multiplication is 16 bits. Because we're going to right shift 8 times, it's going to be back into 8 bits again. So what we're going to do is we're going to multiply the red value by 101 and then say red is equal to red right shifted 8 times. And so we will replace this line here, red equals red times 0.393, with red equals red times 101 right shifted 8 times. You guys see that? So we'll multiply the red value by 101, then right shift 8 times. And that is a fast, cheap, and dirty way of doing floating point math without having to actually have a hardware float unit. And it's probably going to be a lot faster too. Will it always be 256? It'll always be 256 if you're doing unsigned chars, right? So we're doing 24-bit color, right? So the red has 8 bits, the green has 8 bits, and the blue has 8 bits. Right, so that's why we do fractions of 256. Yep. Math came in handy. Yeah, it's surprising. My daughter is studying fractions right now in 3rd grade, and so it's surprising how often we use 3rd grade math. You need a FP to figure out the numerator in the first place. Well, in this case, these numbers came from a website. Right? So the website just has all these magic numbers here, and so we can sit there, you know, outside of the program and just be like, all right, what is 0.393 times 256? Okay, that's 101. Okay, cool. And so we just plug these magic numbers in. 101 rather than 0.393. Will these numbers be given to us for the filter? Yep. Yep, all the magic numbers are given to you. So all you're going to really have to do to do sepia toning is, well, you don't even have to use this trick technically. You could use the VFP, the vector floating processor. I'm just kind of revealing this to you guys because speed is important. You could use VFP and divide. Yeah, that's fine. You could. VFP will be more accurate. It'll probably be slower. Maybe, maybe not. I don't know. It's one of those things. Because you can also use neon. I don't know. Like, you'll probably want to experiment with it. I rewrote the algorithm over and over again, trying to find the fastest one. So this might beat loading 16 chars at once. Probably not. Probably not. But you can do this in VFP as well. Remember, last time there is right shift, right? There is multiply and there is right shift in VFP. So, all right. Catch multiplying two 8-bit values means you need 16 bits of space for the result. Right. Yeah, that's what I was just talking about. So, if you have an unsigned, this should be an unsigned char. This ranges from 0 to 255. When you multiply an 8-bit and an 8-bit number together, you get a 16-bit number. And so I'm storing the result into a short. And so if you're doing this in Neon, rather than loading 16 chars, I'm going to load 8-bit numbers. And then after I multiply, it's going to turn into 8 16-bit numbers. Right? And that will fill up an entire quad word. And then what I'll do is do the vector shift right, and then that will take it back down to 8-bit numbers. And so you can essentially do eight times the performance using Neon, not 16 times, because you need the extra space here. Okay, wrap this in a loop, loading and storing, and there you go. Good. So yeah, so if you're rounding the results, you're going to get probably pretty close to the same answer, or you might just be off by one, and again, nobody really cares. All right, so here is the code for that. I know you guys are all thinking, all right, I got it conceptually now, right? You guys all get it conceptually now, what we're doing here, this trick? All right, I got it conceptually, but how do I do this in assembly? Well, here you go. So this is going to move from D10 into Q. Technically, I don't think you need to do this. I think you can actually just multiply the D registers and it'll widen automatically. So this will move from a D register to Q register. I don't think you actually have to do that. But it's telling it that you're moving unsigned 8-bit numbers. So this is going to widen the data. Do you guys understand what widen and narrowing means? So like unsigned, let's say we have an unsigned char equals 7, you know, and then if we put it into a short, then that's going from an 8-bit number to a 16-bit number. That's called widening. Yeah, so widening is like when you move from a char to a short, or from a short to an int. If you move from a short to an int, that's widening. So anytime you get, because a short is 16 bits, right? And an int is 32 bits. Normally, I always have to qualify that. Normally it's 32 bits. That's widening. And then if you narrowing means going from like an int to a short. That would be called a narrowing operation. And widening is always safe, you know what I mean? Like you can always widen and you don't lose any data. Narrowing, however, can lose data. And so you always have to be careful when you narrow, you know what I mean? So, like, do you guys understand why that's a big deal? Like let's say we had 1,000, like let's say we had short x equals 1,000, and we said char y equals x. This would be a narrowing. Right? Do you guys see that? So a short can hold the number 1,000, but a char can't. So this, let's make it an unsigned char. Y. Okay. When it narrows, do you always have to put it into 2 registers? No, not at all. So here, this is going to do a vector saturating shift right narrowing. So then in there stands for narrowing. And what that will do is it will narrow the quad word to a double word. So in other words, all of the 16-bit numbers are going to turn into 8-bit numbers. And so it's going to shift all. So if you had 1,000 and you did this operation on it, it would shift 1,000 right 8 times. And I haven't explained what saturation is yet, so don't worry about that. Let's go to per. So, decimal 1,000. If we do a right shift, logical shift. If we do a right shift 8 times, then this turns into the number 3. Okay, so if we did a right shift and narrow, then the corresponding register in D10 would have the value of 3 in it, because it originally the number was 1,000. We did a right shift narrow, so the number now has 3 in it. Okay. Will set precision stop us from losing data when you narrow? No, because when you narrow, you lose bits. Like that, you know, you're going from 32 bits here. You got int, that's 32 bits. You're going to 16 bits. Anything that are in the upper 16 bits here go away. Okay. Anything in these upper 16 bits go away. Do you guys understand? So if you try stuffing 1,000, if you try stuffing that into X, it's gonna integer overflow, right? And only the bottom 8 bits are gonna get copied over. And so this is a destructive narrowing conversion. And depending on your C++ compiler, it might warn you on it, or it might not. So let's see, vim narrow.cc, short x equals 1,000. Char y equals x. It's the same thing as saying unsigned char y equals x. So this is a destructive narrowing conversion, right? But after we've shifted right, we don't need 16 bits anymore, right? And so will it be? No, it's not warning on it. Warn all. No. Let's just see out y to get it to shut up about not being used. Let's do clang ++ -w everything narrow.cc. What? Okay. Warn on everything. Yes, there we go. So if I turn on warn all, Clang does not warn about this problem. But remember, guys, wall does not mean all warnings. Even though it looks like -w means warning, right? Even though that should be wall, even wall should be all warnings, it's not. If you actually want more warnings, there's warn extra, of course. And extra doesn't warn about it either, because all warnings with extra warnings on top of all warnings is not actually all warnings either. Instead, for that, you need warn everything. Because right, so the everything warning, though, however, will successfully pick up that this was a implicit conversion losing precision. Okay, so it will warn you here, and if we run it, you will see that We got an extended ASCII character. That's funny. So what we're doing though with that vector shift right and narrow, what we're doing is we're setting y equal to x right shifted 8 times. Right. Let's make this a unsigned short, just for the hell of it. And convert it to an int. And so we're getting the number 3. Okay, like I told you guys before. So if you have 1,000, you right shift it 8 times, turns into the number 3. Yeah. Okay. So do you guys understand narrowing? All warnings is not every warning. Just like DLC, you don't get everything. Yeah. You have to buy the season pass. But sometimes the season pass isn't everything also. You have to get the pre-order pack and the season pass and the Valhalla, Skyrim, Drogar bonus. Super extra elite edition. Yeah. So, Ultimate Collector's Edition that comes with everything except the game. Yeah. I used to have a friend that worked at GameStop, and he would buy like 5 copies of like Arkham Asylum Collector's Edition. I'm like, dude, do you need 5 copies? He's like, well, it's going to go up in value someday. I'm like, dude, nobody's going to want to play Arkham Asylum in 20 years. And I don't know. Maybe. His whole house is just filled with junk like that. And he doesn't play them. He just collects them. So the N means narrow. Okay, so what does saturation mean? Well, in this case, the saturate is not going to do anything. But this is an example of where assembly can do something. What if you didn't narrow? Then it would. Then this wouldn't compile. If you didn't do narrowing, it wouldn't compile. The reason for that is this is 256 bits. That's 128 bits. And so you can't copy 256 bits into 128 bits. Or if it did compile, then it probably would throw away the upper half, right? If you tried moving, like the upper 128 bits would just go away, which is not what you want, all right? So, yeah, your code would break. And so narrowing means each lane. So remember, in Neon, you have 256 bits, and it needs to know how big each variable inside of it is. Is it 8 bits, 16 bits, whatever? And right now I'm telling it it's 16 bits, but I'm going to narrow that lane and the result to 8 bits. And without the narrow, it would copy 16 bits at a time over into D10, and so it would throw away half the data. So narrowing it would go from 16 wide to 8 wide. Because I'm right shifting, right? I'm right shifting. They don't need to be 16 bits anymore. So, yes, that N is pretty necessary there. Shift right, narrowing. So saturation. Okay, so saturation is something that is really cool, and I wish they would have support for it in C++, but they don't. So this is actually one of those areas where you can do something in assembly faster and more awesomely than you can in C++. C++ kind of has no support for it. So what is saturated? Okay, so normally, if we come here into the world of C++ again, and we say vim narrow.cc, and so this guy is what, 3 now. So if we say y is equal to y plus equals 254, what's going to happen to y? Never thought C++ could be garbage. Remember, C++ has to work on every CPU. And so if not every CPU supports saturating arithmetic, C++ is not going to support it. So what happens if we add 254 to 3? What number is it going to end up as? 254, 255. What's 1 higher than 255? Wait, 255 plus 1 is 0. Okay. So if we run this, we get 1. 4, 255. What were we before? So 255, 0, 1. Yeah. Okay. So it has overflowed. Now, this is bad, and this is what we saw with the image processing last time. Is that when we multiplied by 2, the image exploded, right? The areas that were over 128 would wrap around to below 128, and so it made it very alien looking. So the lower areas, it worked fine because it didn't overflow, but the upper areas became darker. So rather than becoming brighter, they became darker. So what if I could tell you in assembly, you can't do this in C++, but in assembly, you could say just cap the value at 255 if it goes over. It's called saturating arithmetic. Okay. Saturating arithmetic. And so what you would do, if you want to do this in assembly, we do something like this. I guess we got x already, so we'll just use x again. X is equal to y. I'll just copy it over. X plus equals 254. If x is greater than 255, x is equal to 255. Saturate. So saturating, it'll go up to the max and stay there. Okay. And then y is equal to x. Okay. So if we do it now, it stays at 255. And if you keep adding to it, it'll stay at 255. So that code here, do you guys see what we did here? So we're adding to y, and every time we add to y, we see if it goes over 255. If it goes over 255, we cap it at 255. And then what if you did this on your whole image? What if for darken, what if we did saturating rather than overflowing? Then what would happen is it would just gradually turn white. As you keep brightening it and brightening it and brightening it, the image would just get more and more towards white until it turned totally white once you turn the multiplier up too high, which is what you want. When you do image processing, if you increase the brightness, you don't want the brightness to go down. You want it to saturate. So saturation is capping at a certain value. Yes, it's capping at the max value for the register. So it breaks your normal understanding of how integer arithmetic works, and it breaks algebra, right? So normally in C++, if you do this, x plus equals 10, x minus equals 10, x will be the same. Do you guys concur? So if I have these two lines of code anywhere in C++, do you concur? X plus equals 10, x minus equals 10, you will get x. Right? Because if it overflows, then it'll just underflow right back. And you know what I mean? So that's one of the reasons why we have overflow and underflow, is so that algebra still works. Right? Because if you look at this, the compiler can look at this and be like, yeah, let's not do that. Right? Because it allows algebra to work. Like the compiler can look at that and be like, no, we don't need to do that, and just discard it. However, if you're doing saturating arithmetic, algebra doesn't work anymore, right? So if these were saturating things, and you said x plus equals 10, and let's say x was 255 before, right, or 250, to make it more interesting, then x would become 255, and then if you did an x minus equals 10, it would drop to 245. So if you did x plus equals 10, x minus equals 10, it would go from 250 to 245. So the algebra doesn't work anymore when you do saturating arithmetic. So that's why by default we don't saturate, so that algebra works. Do you concur? I concur, exactly. So from Catch Me If You Can, one of the best movies, I think. All right, so yeah. But if you're doing image processing, you want to saturate. You don't want to overflow or underflow when you're doing image processing. And that's why on digital signal processors and on the Raspberry Pi and things like that, they have a saturating instruction called Q. Anytime you see Q, that means saturate. Okay? And that will stop you from overflowing. in this case, shift right, you don't need to worry about saturating, I don't think. Because if you shift right 8 times, then you won't ever have anything bigger than 8 bits, because you just shifted it right 8 bits. I put the Q in there just as an instructional thing. Okay. But there's like Q add, VQ add, things like that. So if you do like a VQ add like that, then that would be doing saturating arithmetic. Why is it in the second spot and not the third? What do you mean? Just because it is. That's where they put the Q. So you have Q add, which means saturating arithmetic. It's a different instruction. It's saturating arithmetic rather than regular arithmetic. All right. Okay, so that there will do integer floats. Okay. Q indicates saturating arithmetic. That is correct. Yeah. And ARM32 saturating arithmetic. Matic. So this is what it'll look like. So this is going to load from this pointer. R0 is a pointer, R1 is a pointer. So it is going to load from the pointer 256 bits into Q0. It's going to load from another pointer 256 bits into Q1. And then it is going to do saturating arithmetic. So it's going to write into Q2, Q0 plus Q1. But if any of those values overflow, if they're going to be bigger than 256, 256 or above, then it will cap at 255, right? So if you add 128 to 128, you don't get 0, you get 255, right? And then it stores the results back into another array. So this is going to load 16 chars, add the 16 chars together, saturating them, and then storing the results back into another array. Okay. So that is a saturating add instruction. And so if you want to do saturating arithmetic in C++, then you just make a function in assembly and have your C++ code call the assembly. That's actually a useful thing. So the Neon version is 10 to 12 times faster. So, yeah. Does it only work for 255, or can you do this for any number? It works here. Well, it's 255 because we are working with unsigned 8s. If you're working with unsigned 16s or signed 32s, it saturates at whatever max int is. Right. So for a signed 32-bit number, if you add together 2 billion plus 2 billion using saturating arithmetic, then that value would be max int, which is 2.1 billion, right? So if you add 2 billion and 2 billion, you get 2.1 billion and change. It'll saturate at whatever the max is for that bit, the number of bits you have. This would be pretty cool if your CPU used ARM. Intel saturating arithmetic. I didn't spell it right. Yeah, you can saturate on Intel as well. Again, using their version of Neon. So Intel has something called MMX and SSE and SSX and stuff like that. And so they do, the MMX stands for multimedia extensions. And so image processing is one of the things they do. So on an Intel, you do saturating arithmetic there as well. Okay. Sound cool, Zach? Zach Hazard. And it's also useful if you do multiplication, right? Because multiplication can saturate. You can explode really easily with multiplication. So you can do cumul as well, which will do saturating multiplication as well. Okay, all right. We're talking about floating point numbers because they're slow. Yeah, all right. So, and because they're not part of ARM by default, you have to have a optional add-on for them. So, your regular registers are 0 to R15, but if you've got VFP support, then you've got single point floating point registers, S0 to S31. You've also got, if you've got neon, then you got D0 to D31 and Q0 to Q15, with Q0 to Q15 being the same registers as D0 to D31, and D0 to D16 being the same registers as S0 to S31. So these guys are the upper half of these guys, and these guys are the same thing as these guys. And so just be careful when you're switching back and forth between single point precision, single floating point precision registers, double floating point precision registers, and quad registers, because they're the same registers. They're not actually different registers. They're the same registers with different names. Remember, Spider-Man meme. Okay. So we got the real deal Holyfield here, and got an image of those and how they align. Was that in the slideshow? Yes. That was right here. This is actually a really important slide. And unfortunately, you know, the documentation on neon is not very good. And so, like, when I first started teaching this class about 5 years ago, I had to learn it myself, and I was just like, oh man, this is rough on students, you know, because like it's not very good documentation out there, you know, and that's why I've put together all these slides for you guys, just so you can kind of, you know, where was this found? I don't know, like on some website. Did I cite it? No, of course not. What a great academic I am. All right. So, yeah, so the S registers are the upper half of the D registers. So D0 to D15 are the S0 to S31. And D0 to D31 are the same thing as Q0 to Q15. So if you write to Q0, you're going to overwrite D0 and D1, and S0, S1, S2, and S3. So just make sure that you don't clobber yourself, right? That way, because they're the same registers. They're the same registers, so just be careful. And are they preserved through function calls? I don't know. I've seen conflicting things on that as well. All right. That's why they won't let you know you. That's why I can't take my own class. I had to learn about floats to work for learning fast inverse square root. Yeah, we're going to learn that today, probably. Okay, so here is how the IEEE 754 format works. Let me turn off the camera again so you can see the whole slide. There we go. So the IEEE 754 floating point standard is the sort of the industry standard for how floating point numbers are actually represented. I guess there's probably other standards as well, but nobody uses them. Okay. So if you have a, what is this, 32-bit number, right? This is a total of 32 bits, right? 32 bits. This is very different from how ints work, right? With an int, you have, you know, the 1's bit and the 2's bit and the 4's bit and the 8's bit and the 16's bit, and then the top bit is like negative 32, right? If you're talking about 2's complement. With 2's complement, whatever the upper bit is the negative of what it should be, right? And that's how signed arithmetic works. Completely different for IEEE 754. It's completely different. The way that it works is very different, and so you kind of got to learn it. You kind of got to learn it. So it has a sign bit. Okay, so there, you know how we talked about how it's stupid to have a sign bit on a normal integer, like if this was just plus and minus or whatever. Now it's dumb because then you could have positive 0, you could have negative 0. Remember how we talked about how stupid that would be? Guess what? You can have positive 0 and you can have negative 0 in IEEE 754. That's a thing. You can have positive infinity and you can have negative infinity. That's a thing also. So, yeah. And so you can have positive 0 and negative 0. The thing is set so that if you clear the whole thing, if you set the whole thing to zeros, like if you do memclear is a function that zeroes out a bunch of memory, right? So it just sets a giant chunk of memory all to zeros, and it can do that potentially in fast time, right? So for that reason, if the sign bit is 0, it's a positive number. That's actually a positive number. So if the sign bit is 1, it's a negative number. Okay, and the reason for that is because memclear is designed to just zero out memory. And so when 754s get zeroed out, they're just positive 0, the normal 0. Okay. All right. So then, have you guys ever seen scientific notation before, where you've got like negative 10.2 times 10 to the 5th? Have you guys seen that before? In I know Dolio. Okay. All right. Maybe. Don't remind me. Well, several times. All right. Cool. So that is basically how the system works. Okay. So IEEE 754 is scientific notation. That's how it is. So it's binary scientific notation. So the exponent, sort of the equivalent of the 5th power here, is that. And the mantissa is kind of that. Conceptually. How it actually works, we're going to learn in a second. But do you guys kind of see that? Yeah. IEEE. Yeah. That's how you pronounce that. It's the International Electronic Engineering Association. So do you guys kind of understand, like, 7.3 times 10 to the negative 10th, something like that? So the exponent would be kind of like that part there. And the mantissa is this part. Association. Right. What does it stand for? They're a really important organization. My dad subscribed to them for years. I've read their journal. Institute of Electrical and Electronics Engineers. There you go. How many members? 419,000 members. Yeah, IEEE is really important. Okay. So, yeah, that's kind of 10.2 is valid scientific. So if you wanted to just say 10.2, it'd be 10.2 times 10 to the 1st, right? So this part is the mantissa, that part is the exponent, but the actual details we will cover in a second. Okay, so yeah, okay. So before do we have fractions? Yeah. Let's talk about the fractions first. Okay. So you guys all know how like a normal binary number works by now, right? You have the 1's bit, the 2's bit, the 4's bit, the 8's bit, the 16's bit, right? You guys all know this, right? Times, yeah, you're right, times 10 to the 0. That is correct. But it's been erased, so there is no evidence of my error. Except on YouTube. All right. So, you're absolutely right. 10 to the 0th. Correct. So, what we have here with floating point numbers is that we just continue this trend to the right. So, if you have a decimal number in binary, let's say you have this. Let's say I gave you in binary 10010.1. This is the 1/2 digit. This is the 1/4 digit. This is the 1/8 digit. This is the 1/16 digit. 1/32 digit, and so on and so forth. Okay. So this number here would be 18.5. Do you guys see that? the little decimal there? Do you guys see that? It's not like programmers are mathematicians. Yeah. I also haven't had enough coffee today. Say it again. Sure. So let's say I gave you this number, DeBello, 111.01. See how there's a decimal now? There's a decimal. So the decimal represents, where a decimal is. And so what number is this, DeBello? 111.01. Yeah, so the upper half here is 4 plus 2 plus 1, which is 7. And then the area below the decimal, that is a 1 in the quarters digit, so that is 0.25. And so this number would be 7.25. Okay. You already explained it better than the book, in my opinion. Thank you. Thank you. Makes up for Dolio criticizing my lack of math skills. All right, so let's do... let's do another one, 0.111. Miss Tran, you want to take this one? Somebody has to be cynical. No, it's a fair criticism. Yeah, especially when I'm lacking coffee. .875. So yeah, that sounds right to me. 0.5 plus 0.25 is 0.75. 0.75 plus 1.25 is 8.9. Wait, 8.75. Yeah, that's correct. 0.75 plus 1, 2. Yeah, 8.75. Yes, good. So yes, very good, very good. Faster than I figured out. So that is 0.875. Okay. Your calculator's always correct. Yeah, that's fair. Here I am trying to do it in my head. So if we have programmer mode and no decimals, so disappointing. So much disappointment. Programmer mode. Can't do decimals. What kind of programming mode are you? Okay, so how are you calculating the decimals? So this is the 1/2 digit. That was the 1/2 digit there. That's the 1/2 digit. That's the 1/4 digit, and that's the 1/8 digit. So with a 1, it's 1/2 plus 1/4 plus 1/8. So we're just continuing the same pattern of how binary works, just into fractions. Does that make sense? Would that be 1/4? Do we have to do common denominators, or is that all there is? That's it. Yeah. So yeah, let's do another example. So if DeBello, let me give you one. Let's say 101.0101. Yep. So DeBello, you can figure out the upper bits the normal way. So DeBello, what are the upper bits? 5. Good. And then the lower bits below the decimal. This is the 1/2 bit not set, 1/4 bit, 1/8 bit, 1/16 bit. So how do you figure this? It's 1/4 plus 1/16. What is that? So you do 0.25 plus 0.625. Yeah, that's one way you're doing it. Or you can... Ada, what is 1/4 plus 1/16? I need to use a bathroom. Or you can just observe that this is... Where's my mouse? There we go. You observe this is 5/16, right? Let's do it that way. 5 divided by 16 is 0, because we're in programmer mode. Cool. 5 divided by 16 is 0.3125. Yep. So the answer is 5. Why do we keep doing that? 5.3125. And that's how we do decimals in binary. It's pretty easy, right? But that's taking me ever fraction and adding them together. Yeah, I mean, computers do that for free. So. Okay. Do you guys need any more examples using binary decimals? That's how you're supposed to do this? Yeah, that's how I do it. If I asked you on a homework assignment, compute 11.11, you'd just be like, all right, that's 3.75, whatever. You guys all got that? Does that make sense? Okay. All right. So Dolio, let's have you see if you can figure it out the other way. So if I give you 7.75, Dolio, what is that? .11. Cool. Yeah, that's pretty easy. All right. All right. So Dolio, convert 1/3 into binary. Just continuing the exponents of 2 in the negative direction. That is absolutely correct. Yeah. So Dolio, yeah. So yeah. So 1/3 cannot be represented in binary, right? You can never actually approximate. You can never actually approximate a third using powers of 2. So if we were to come over here.
The question again?
What is 1/4 plus 1/16?
1/4 plus 1/16.
She left. Right. So
I give up.
you give up. It's 5/16, girl. It's 5/16. Yeah. We're doing fractions in class right now.
Okay.
What is 1/2 plus 1/4?
1/2 plus 1/4.
If you have half of a pizza and I give you another quarter of a pizza, how much of a pizza do you have?
Well, you're one half and
A half and a fourth, yeah.
it's like two-thirds.
2/3.
Or
3/4,
3/4.
yes. That's right. Good. All right. So yeah, so a third cannot be represented. Well, if we go up to double precision, we get more precision out of it. See, before we had this. So with a float, we got one. With a float, come on, just let me select a letter. Okay. We got seven digits of precision before we got error, right? And then with double, we got the full 16 bits. But if we were to turn the precision up higher, then you'll notice errors creep in after the 16th digit. So that's pretty common. Floats give you about 6 or 7 digits of precision. Doubles give you about 15 or 16. If you need more, there is the MPF library, the GNU multi-precision float library that can give you 50 digits or 100 digits of precision. And if you're going to be shooting something to Mars, I would recommend doing that. Okay, so that's why floats are so weird. Yeah, so powers of 2 can be represented in accurately in decimal binary, but power, division by 3, things like that cannot. They will always have error in it. Okay, so why does this matter? Well, why does this matter is we first have to convert a number into decimal binary. So if we took, if we said 100.1, Actually, that's kind of annoying. Let's just do 7.75. Okay. Then this would be 111.11, right? So what we do, it's like scientific notation, right? If you had 103.75, this would become 1.0375 times 10 to the second, right? Do you guys see that? With scientific notation, you move the decimal over there, right? You guys remember that? Moving the decimal. Wouldn't it not be binomial? It's the decimal is the name of the dot. Yeah. The binomial. Yeah, I like it. I like it, Rivera. It's a good name. That's why my calculator adds a random 0.001 when solving integrals. Yeah, that's where error creeps in. It's because some things you can represent perfectly accurately using floats, and some things you can't. And so, if you one of the benefits actually of knowing IEEE 754 format is that you actually know what is safe and what won't have error in it, right? So like, if you say float f equals 2.5, this will actually be saved exactly. There is no error in this. And if you multiply this by 2, there is no error in the result there either. Hopefully, right? But if you were to try and do like anything that was like a third or something like that, then it will be inaccurate. And so when you understand these things, then your C++ knowledge gets better. And that's a theme that I've been kind of hammering this entire semester, is that you're not going to be packing bits and making IEEE 754 numbers, but you're going to be using floats and doubles all the time in your C++ career, right? And so knowing how many bits of precision you have, knowing how many bits of precision you have in the exponent, even if it's not like, like you've memorized the max float and things like that, even if you have just kind of a general idea of like where the limitations are, then you will write better code. You will write code that has less bugs in it. Okay? Less error. So what happens? Okay, so what happens is when we have a binary decimal number like that, then you move the decimal to the first, after the first digit. Okay? And you keep track of how many shifts you did, and that becomes the exponent. So if I were to tell you guys convert 0.125, you've been learning Go and writing Java for Minecraft, and you've noticed your code's way better than after you take this class. Yeah. I mean, I don't know. Java. Yeah, probably. Like kind of when you know what's happening under the hood, like it's not guesswork anymore, So what is 0.125 in binary decimal? Binary decimal, right? Structuring the code better, yeah, that helps too. Yeah. So what is 0.125 in binary? Hazelton is correct. It is 0 in the halves digit, 0 in the quarters digit, and a 1 in the eighths digit, right? Write a Go AI that could play Minecraft in Java. You should write in Go a Go AI. Right, so this would be this. And so if we were going to convert this to scientific notation, where would we move the decimal? Should we move the decimal to the left or move the decimal to the right? Which way should this decimal move? 3 to the right. Okay. So the decimal should go 1, 2, 3. There. Now, one thing that, let's do one more example. Let's do, so this would be like, this is the same thing as 1.0 times 2 to the negative third. You guys understand? So that number and that number are the same. Okay. So let's do 10.5. So what is 10.5 in binary decimal? What do you guys think? 1010.1. Very good, guys. Very good. Well done. So, Guerrero, which way do I shift the decimal and how much? The dot. So Rivera won't complain. It's a decimal. It's a dot. Very highly scientific. Does it have a better name than that? I don't know. So Guerrero, which way do I shift the decimal point? 3 to the left. Very good. So if I shift this 3 to the left, 1, 2, 3, then this number is the same thing as 1.0101 times 2 to the third. Do you guys see that? Does that make sense to you guys? I'm going to give you a worksheet on this, so hopefully it does. All right, so one thing in common is that you shift the decimal until it is to the right after the first 1 in the number. You guys see that? So wherever you end up with a 1 dot, right? So big observation they made, you don't need to store the 1. Okay? Because it will always have a 1 there for every number except for 0. And 0 is just defined as all zeros. Easy. It's a special case. Because there will always be a 1 at the beginning of the mantissa, you don't actually save it into the number. That gives you an extra bit of precision. Okay. So when you write the mantissa down, you actually just write down 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. And for the exponent, you're going to write down 3 with one very important thing, because you're not going to write down 3. But do you guys get this part? So the bits for the mantissa are going to be 0, 1, 0, 1. For this one, the mantissa would be all zeros. For this one, the mantissa would be 0, 0, 0, 0, 0, 0, 0, 0. Do you guys see that? Because you do not need to save the 1, because there will always be a 1 there. The 1 will always be there. And so for the exponent on this one, the exponent for this one is going to be -3, right? Except it's not. I'm going to show you on the next slide. So the mantissa is all the bits after the first 1. So we'll do one more. So let's do 1/16 plus 1/32. And so in binary decimal, this would be 0.1/2, 1/4, 1/8, 1/16, 1/32. Okay, so you're going to shift the dot 4 points to the right, and you're going to get 1.1 times 2 to the -4th power. So when you write out the mantissa, you're going to write down 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. It's 0 extended to the right. Right, it's like you could write 10.0 or 10.00 or 10.000 or 10.000, but we don't. We typically don't write all those extra zeros to the right of the decimal point, right? Just like we don't write leading zeros to the left either. We don't write, when we're writing the number 500, we don't write 000,500.00000. We drop zeros to the left, we drop zeros to the right. But when you're writing it into a register, all those zeros are there, right? So the mantissa in this case would be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? 24. The mantissa is 24 bits, so 23 bits. Sorry. So you have a 1 followed by 22 zeros. Okay. So the mantissa is everything after the point. It's everything after the point. All right. Because the thing before it is always going to be a 1, so you don't need to write it. You don't need to write it down. Okay. Now for the exponent I said is 3. That's a lie. The exponent is actually they bias the exponent. And the reason why they bias the exponent is because they don't want to worry about negative numbers in the exponent. So what they do is they add 127 to it. And the reason for that is so that you can't have a negative number in the exponent, basically. So if your exponent was 3, what you're actually going to write down is 130. Okay. So that is 1, 0, 0, 0, let's see, 128th bit, 64th bit, 32nd bit, 16 bit, 8 bit, 4 bit, 2 bit, and 1's bit. There. And so the actual exponent you're going to write down is 1, 0, 0, 0, 0, 0, 1, 0. So if the exponent was 3, like on the next slide here, we had the exponent of 3, then what actually gets written down is 1, 0, 2. Right? Okay. And so that is IEEE 754. Add or subtract 127. You always add whatever your exponent is. You add 127 to it. So if your exponent, like on that other example, was if the exponent was -3, then what you're actually going to write down is 124, right? Which would be 64 plus 32. 124 in programmer mode. 124 in programmer mode is all ones. No, that was 127. That was wrong. I could tell because it was all ones. Okay, it's 5 ones and 2 zeros. Okay. So this is what would actually be written to the register. So that part would be the E. The mantissa would have what was it, 1 0 0 0 0 0 0 0, and the sign bit would be, if it was positive, it would be 0. So that's the whole thing that gets written. Okay. I'm not really sure how that's supposed to vet for negative exponents. Well, if the exponent was -3, right? And so if we add 127 to it, then we get 124. So you don't have a negative number written to disk. What if it's positive? If it was positive 3, then you write down 130. When it's overflowed, then you overflow. Right. So the exponent has to, the exponent can only range from negative 128 to positive 127, 128, something like that. So the exponent is 8 bits, so 255 minus 127 is 128, so the highest value can be 128. And the lowest value is negative 127. So that's the range you can have there. All of them grow by 127. You add 127 to whatever the exponent is. So 127 plus -3 is 124. 127 plus 3 is 130. So that's the actual bit pattern written to disk. And the reason, it also makes the math easier on the VPU, FPU. Sorry. So let's do an example. Okay, let's do an example. So we're going to convert the number 3 to floating point. Okay, so the sign is 0. So if we're going to write down a 32-bit number, the first bit is the sign bit. That's 0. It's a positive number. It's easy. Next, we have to figure out the exponent. What is the exponent here? How many times do we have to shift the decimal? What do you guys think? 0 times. Pretty easy. So 0 plus 127. I think that's wrong, actually, isn't it? Oh, no, because we have to convert to binary. Right, yes, thank you. Right, so convert 3 to floating point. So it is 11, right? And so we have to shift the decimal 1 point. So that is an E of 1. So in other words, if we convert this to scientific notation, 3.0 is the same thing as 1.1 times 2 to the first power. Do you guys see that? 1.1 times 2 to the first power, same thing as 1, which is the same thing as 3. Okay. You guys with me so far? Okay, so with the exponent of 1, we add 127 to that, and we get e is equal to 128. So the bit pattern we write down there is 1 followed by 7 zeros. 4. Okay, so the exponent section looks like that. The sign section looks like that. And then the mantissa is everything after the decimal. So the mantissa is that. So it's 1 and then all the trailing zeros. Dot, dot, dot. 22 zeros. And that is what is written to disk. If you open it up in a hex editor and you, like if you write a float to disk, that's what you'll see in bits. Can you say the E part again? Yes. So the exponent in scientific notation is 1, right? Because 1.1 times 2 to the first, so the exponent is 1. So what gets written to disk is it adds 127 to whatever E is. So 127 plus 1 is 128. And so that's why you see 128 written here. Okay. So the computer basically reconverts it when it's reading, yeah. So this is the bit pattern that will get written to disk or is in a register. And then anytime it gets displayed, there is code in C++ that pulls out all this stuff, and in C++ it'll render it as 3.0, right, or just 3. Floats don't overflow. Don't they roll to infinity? Yeah, they don't overflow. They can, but it's a pretty big number, right? To overflow a float, you have to have a really, really big number. Okay. Oh, I see. Do they go to infinity? Yeah. We'll go over infinity and nan and -0 in just a second. Let's just go over the regular cases for now. So so this is what gets written to disk, like if you're going to output it, or if you have a debugger and you're looking at the values in a register, especially if you've copied a float into like an R0 register or something like that, and you're looking at it in GDB and you're just like, why the hell is this the way it is? Right, because GDB would actually display this, like if you were displaying the register values in hex, GDB would display this as 4 0 4 0 0 0 0 0. So if it in GDB it would display it like this, and you're like, I thought it was supposed to be holding the number 3 and it's holding the number 4. It's 404. What the hell? Not found? Number not found? I don't even know what's going on here, right? And so, yeah, if this was -3, if this was -3, that would be a 1, and so this would be 8 plus 4, which is 12, which is C. Yeah, yeah. A is 10, B is 11, C is 12. So this would be displayed in GDB as C04. And you just be like, what the hell is going on here? You know, and so I was actually doing something that needed me to be in GDB, looking at values while I was taking this class, and I was baffled, and then I literally went to class the next day and they explained this, and I was like, oh, get it now. I get it. You know, it's not buggy at all. It's the right number, you know. College is useful. Who knew? And this is, again, one of the reasons why it's a good idea to go to college, because this is not the kind of stuff that, like, if you're a self-taught programmer, most self-taught programmers, I have met some that have studied this, but like most self-taught programmers, just why would they study this, you know? But it comes up, you know. So the yeah, so this would be, if you saw that in GDB, you could just look at that and be like, oh, that's -3. All right, so let's do 3.25. Okay, without revealing it, we'll take it from the top. Alan, are you here? Alan, are you here? Okay. So what is 3.25 in? What is 3.25? Oh, look at that. In slideshow mode, it's completely different. Okay, what is 3.25 in binary decimal? It is 11.01. Yeah. Okay. So write that in binary scientific notation format. Yep. So 1.01 times 2 to the first. Okay, so the sign bit is what? The sign bit is what? Is it positive or negative? 0, very good. And then the exponent we'll get to in a second. And then the mantissa is what? What is the mantissa? 101. Good. It's everything after the dot. So the mantissa is going to be 101 followed by a bunch of zeros. And the exponent is 1. And so what do we... 1 plus 127 is 128. So it's going to be the same as before, right, Alan? 1, 2, 3, 4. And so, do you concur? Does that look good to you? Good. All right, so eraser. No, no, okay. Lasso select. Delete. There we go. All right. So, yep, that's what we got. So, very good. Round of applause for Mr. Allen, please. So, sign bit 0, exponent is 1 and 7 zeros after it. Mantissa is 101 with all zeros falling. Okay, so the next one is 8.25, and so for that one, you're going to have to shift it a few more times. So, 8.25 is 1000.01. So we shift the thing 3 times. So this is 1.00001 times 2 to the 3rd. So the mantissa is going to be 001. So you can see down here, 001. And the exponent is 127 plus 3, which is 130. And so it's 128 plus 2. All right, so double precision is essentially the same thing as single precision, except you've got more bits for the mantissa, you've got more bits for the exponent. And in recent years, actually, this may sound weird, they've added half precision. So you would think that like 16-bit floats, like an F-16, not the Fighting Falcon, like not the plane, but float 16. It's actually a fairly recent addition. So this is called a half precision float. And that's been added recently. And the reason why it was added is because in computer graphics, you don't need that much precision, right? If you do half precision floats, you can get a frame rate increase, and you might see a small bit of noise. You know, like if you do half precision colors and ray casting and things like that, you might see a little bit of noise in it. But if you can get more frame rates, frame rate matters a lot more than quality usually. So there is half precision floats now as well. Okay, so let's talk about special cases. So there is positive 0 and negative 0. Positive 0 is just all zeros, right? And that's again because mim-clear. Typically, if you have like a giant array, you got a giant array, and a lot of times you just like set it equal to 0. And so mim-clear will just come in and zero out the entire thing. And so if you mim-clear an array of floats, they're all set to 0. Nice. Negative 0 has a 1 in the first bit and then all zeros after that. So that's a special case there with a 1 with all zeros after that. That's negative 0. Holy, this class went by quick. Yeah, time flies when you're having fun, dude. If you have all 1s in the exponent and 0s in the mantissa, then you've got positive infinity and negative infinity. And then there's 2 different kinds of nans as well. A nan comes about when you have division by 0. If you say 5 divided by 0, then you get nan. Nan stands for not a number, or Native American nations, or grandma, one or the other. Usually in computer science, though, it stands for not a number. And so if you divide 5.0 divided by 0, you will get nan. And there's 2 different kinds of nans. There is a signaling nan or a quiet nan. So a signaling NAN will throw an exception usually and kill your program unless you catch the exception. A quiet NAN will just not. And so that's really kind of an implementation specific feature that you don't need to worry about. Just be aware that if you divide by 0, it can throw depending on how your system is set up. So yeah, here's the chart of all the different specials and things like that. But basically, like I was on Skyrim the other day, and they had a free armored mud crab companion that cost $0, and it was 100% off. And so the new price was $0. And so to compute the discount, the PlayStation Store did $0 divided by $0, and it displayed the price of the armored mud crab companion as NAN. And I took a picture of that and posted it on Discord the other day. I like going NAN hunting. You're at the airport, and when the estimated time of arrival of your flight is NAN, that's a bad sign. It means the plane caught on fire, right? Which I saw happen once. I was at Vegas, and I'm looking out the window, and the plane on the tarmac catches on fire. And that was exciting. I was on U.S. Airways back before they went out of business. Who knows why? Maybe it's because their plane's caught on fire. And I'm just in there watching like all these fire trucks start coming up, and they're spraying the back of the plane. Like something in the luggage burst into flames. And I was like, man, I hope that's not my plane. You know? And it wasn't. But there were some people like, hey, do you know when the flight to, what was it, Santa Barbara is leaving? I'm like, I don't think that flight's going to leave, dude. Why not? That's your plane there. The one that's burning, that's your plane. Yeah. I mean, it was a little ungracious of me, but I did point out, like, you should probably just not expect to have a plane because it's literally on fire right now. And then on that flight taking off from Vegas, the railing of the luggage rack detached and hit me in the head, and I started bleeding during takeoff. I'm like, and the stewardess comes running off because we're taking off. She's like, what's wrong? She sees me with like blood on my scalp and stuff like that, and she's like, oh, I'm so sorry. And she takes this metal rail, she stuffs it back up into the luggage rack, and then runs back to her seat, and then the thing detaches again and whacks me in the head again. It's like, cool, thank you, U.S. Airways. I'm glad you're out of business now. Bleeding. And she's like, sorry, you can't come up again. We're taking off. Like, thank you. Thank you. You could have gone me a Band-Aid or something. I don't know. Good times right there. So, all right. So, yeah, there are some special cases with floats. If you have all zeros in the exponent, then that indicates a denormal. And so a denormal doesn't have a leading 1 in the mantissa. You do that if you have really small numbers. Like if you're trying to represent 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, if you were to drop the leading 1, then the exponent might be too big to fit into the exponent, right? Because you have less precision in the exponent than you have in the mantissa. And so if your exponent, if the bit pattern in the exponent is just 0, 0, 0, 0, then you can actually get 24 bits of precision out of it, because the mantissa is just going to hold the actual bit pattern. And so for very small numbers, it'll go into denormal mode. Denormal mode means it doesn't have an exponent. It's just the bits are the bits. And so you can do that to represent very small numbers with more than 8 digits of precision. And yeah, and that's it. So you've got signaling NAN, you've got quiet NAN, you've got negative normal numbers, which just has a leading 1. You got regular normal numbers that are positive, positive infinity, negative infinity, positive infinity, negative infinity, positive 0, negative 0, positive denormals, negative denormals, and there you go. So that's the IEEE format, and the CPU has to handle all of those cases. If you add, if you add 5 plus NAN together, you get NAN, right? And so that's one of the reasons why ARM does not support floating point numbers out of the gate, because the thing is complicated, yo. It's complicated. See, boy. If you're trying to do silicon to do all this stuff, you have to handle all of these special cases in silicon, and that's complicated. And so by default, ARM CPUs do not handle floats because it's complicated. How do you handle positive and negative 0? So double precision has 11 bits of exponent instead of 8, and has 52 bits of precision instead of 23 in the mantissa. And then there's extended precision, which is a 79-bit number. I don't know what that is. I've never seen that. But for more precision than that, I use the GNU multi-precision float library. And that handles my 100 digits of precision needs. Okay. So that's our lecture. Okay. So doubles are basically the same thing. It's just they can handle 8 times the range of exponents, and they can handle way more precision in the mantissa. They still have positive infinity, negative infinity. Okay. So we'll put up a worksheet for you guys that'll be due on Tuesday, and then I'll push out the sepia toning assignment at some point. Okay. GG easy. That's floats, guys. Another blanket has been removed, and the inner workings of the CPU is exposed on a YouTube video. The truth is out there. All right. You guys have any questions? You can take off. It's fine. All right, cool. I'll see you guys later.